Okay, we haven't had that fire test or alarm test yet, so I'm going to proceed with example 2. And let's take a function equation and we're going to analyze it for its concavity. So we have f at x equals x to the fourth minus 8x cubed. Okay, so we have a quartic equation, a quartic polynomial function. So if we look back upon where we've been and what we've done, the first derivative was relevant in this particular lesson because it was stated, and if you look back with me on this, okay, let's just take a moment and go back, that f prime at x was mentioned here in terms of where the tangents are increasing. But more importantly, what we'll do is use the first derivative right now in order to figure out the second derivative. Because if we can figure out where the points of inflection occur, that is where the x values are, also known as critical numbers or critical values, then we can figure out the concavity. So let's do that. Let's figure out the first derivative at x. Okay, so we're going to apply that to this term, and we're going to end up with 4x cubed, and then followed by this term here, minus 8x cubed. The derivative of that would be minus 24x squared. Okay, let's go ahead, let's find our second derivative. So f double prime at x is going to be 12x squared minus 48x. Okay, so far, so good. Let's then try to apply this definition here. Okay, so if we can set it equal to 0 and solve, then we're going to end up with points of inflection. So we're going to set the second derivative at x to 0. And in doing so, remember all of the things you've learned over the last few years in solving quadratic equations. Our first tactic is to factor. So let's pull out a 12x, and we'll be left with an x minus 4 as the remaining factor. So this is very important, okay? Because when we create a table for summarizing the concavity of a function, we're going to list its factors along the left-hand side. So when we now look at the solution to this equation, okay, there are two of them, 0 and 4. So we can see that x in this case belongs to a particular solution set, and that is 0 and 4. Okay. These values are also critical numbers. Okay, points of inflection will occur at the x values that we have here. That is at 0 and at 4. So what we'll do is take these critical values and we're going to set up intervals. Okay, these three specifically. Those intervals are going to comprise where the graph is concave up or concave down. So for instance, let's visualize. Let's just say, for instance, that, well, this is not the graph, obviously, but the intervals are going to correspond to regions where we have concave down, right? And it's going to correspond to regions where we have concave up, which we've already identified, say here. Okay, so let's go back and let's finish this off. Getting a little ahead of myself here. What happened to that particular page that we were working on? There we go. That's what I needed. Okay. So what we'll do is we're going to test some values. So for instance, let's say that we use a number less than 0. Let's go minus 1. That'll make it simple. Let's go 1 here. And x bigger than 4, we'll go 5. Okay, so testing those values in each factor. So let's start with 12x. Multiply by minus 1, and we're going to have a negative value. X minus 4 will be negative. The sign of the second derivative, that is two negatives, right? Being multiplied, right? Check out the operation right here. We're multiplying. We're going to have a plus. Let's continue on. If x is 1, 12x is positive, x minus 4 is negative, f double prime at x negative. Lastly, bigger than 4, such like 5, positive, positive, and positive. So what that does for us is, if we look back on our definition for concavity, okay, which we had right back here. If the f double prime at x is positive, the graph is concave up. Negative, it goes down. So positive, let's head on back here. So if it's positive, it is concave up. You'll notice that I had to pause. There was a bit of a brief pause in the video as the fire alarm did go off. Hopefully it doesn't sound again. Let's get back to it. So f double prime at x positive, meaning that the graph is concave up. So we're going to see concave up, meaning as such. Okay, where it's positive again, concave up, and here concave down, where the second derivative is negative. So let's look back on what we were asked to do, and that was to find the intervals of concavity for f at x equals x to the fourth minus 8x cubed. So what we can then say is based on the results of the table. Okay. So therefore, f at x is concave up for all particular x values corresponding to this or these intervals. So 2 minus infinity up to 0, or from everything from 4, not including 4 of course, and onwards. And then we'll say that semicolon concave down for all x belonging to the remaining values. And that is between 0 and 4. Okay, so now that we've finished that second example, we're able to move forward and to account or learn more information. Okay, so there was one note mentioned earlier about the possibility of inflection points. And I'm just going to give a couple of examples. You're welcome to look up more. But some functions can change concavity without having inflection points. So that should say without here, not with. So in these cases, you might see, for example, rational functions like the one we have here, that concavity changes around VAs or discontinuities. So for instance, if you study this graph, you can see there are VAs at x equals 1 and x equals minus 1. So you can also see that around these VAs, the concavity changes. But the values of 1 and minus 1 are not considered points of inflection or values where the function inflects because those values are not in the domain, right, of the function. Something else to consider too was in that previous example, we noted that we had an interval of concavity followed by another one. Okay, they were slightly separated in terms of one was higher than the other. But what you need to take note of here is that this function at this particular location doesn't have differentiability for the reason that the tangents reach what we call a vertical tangent. So from either direction, you can kind of see that occurring. So when there's a vertical tangent, we call this particular point here, this is known as a cusp, or that is the shape of the graph. It's a cusp, and at cusps, the functions are not differentiable. So if we can't find the first derivative, then it would make sense that we cannot find the second derivative. And without a derivative, first or second, definitely second, because according to this test, f double prime at x equals 0 at points of inflection. And that's just simply not going to be feasible for that particular example. Okay? So there is another way to determine concavity and also to establish what is a local or local min or maximum value. So let's just say that we have a function f that is twice differentiable over an open interval. Okay, so it's not closed on either ends of the interval. And there is a number c, critical. Just like we had a was a critical value before, c is the critical value now. So the first derivative at c is equal to 0. Okay, and recall what that meant graphically was we had a horizontal tangent. And you'll remember having done that and seen that in the last section on maximums and minimums, where the local maxes and mins represented turning points to the function. Okay, but this time there's a little bit more to it. Okay, so if at that critical value, if at f double prime at c, the value of the second derivative is positive, then we have a local min. Okay, if f double prime at c is negative, we have a local max. Okay, and these points also came up in that last lesson. You might remember that specifically in the video that was done and the handouts that have been provided online, that the second derivative test can tell you if you have a max or a min. And if at that critical value, if at the max or the min, you have a second derivative equal to 0, or if it doesn't exist, you may have a local min, a max, or neither. Okay, so in that case, what we do is we then go back to the first derivative test, which is this one up here, in order to draw a conclusion. So right now, we're going to go back and do the same example, but a little bit different. Remember that in the first part, or example 2, we had to account for where the function was concave up and where it was concave down. Okay, that helps us to establish the shape of the function. What we're going to do now is we're going to find the local maxes and mins, and that's going to give us all the depth, right, or the heights, the lows, just how low those valleys go and how high those hills actually reach when we're going to set up our graphs. So let's go ahead and do that. Okay, local max and min values of this particular function. So what we need to do is establish where, right, where f prime at c is equal to 0, right? Let's play off this definition here. So our first derivative at x was 4x cubed minus 24x squared. Okay, so what we'll do is let's factor this down, and we'll pull out a 4x, and specifically a 4x squared, and then we're going to be left over with, what do we have there, folks? A 6, right? X minus 6. So what that implies is that the solutions to this equation right? So the solution set, there's only two values that make the 0. So 0 or 6. So take note that the 0 is here, and then the 6 produces a 0 here. Okay, so we know the critical values, 0 and 6, where the function turns. Okay, we just don't know if they happen to be a local min or local max. So let's go ahead and figure that out. Okay, so let's apply these ideas here. Okay, so let's determine our second derivative, which we had already written down previously, and it was, what do we have? 12x squared minus 48x. And its factored form, if you recall, was 12x on to x minus 4. So, applying those rules, let's determine f double prime at the critical value 0. Okay, so what we're going to have there is 12 by 0 by negative 4, which is 0. Well, what that means, right, based on the information above, is that it's inconclusive. So, possible inflection point, but we're not sure. Okay, so we're going to come back and test that a little bit further. On the other side of the fence, we're going to test at 6. So let's throw in 6 into the equation for the second derivative. And we're going to end up with, what's this, 72 multiplied by 2, or 144, which is positive, greater than 0. So that implies that we have a local minimum. Let's just double check. Yep, there we go. We have a local minimum at x equals 6. Okay, or at c equals 6 or x equals 6. So that is the x value for it. If we're to determine the actual value or the point of it, then we'd have to go a little bit further and we would have to set x equals 6 into f at x, or the original equation. So then f at 6 would then be, let's go back and get that equation again, x to the 4th, so 6 to the 4th minus 8 times 6 cubed. Let's double check. And we'll have to do some fancy multiplication, or we'll take the easy road here and we'll grab a calculator. So 6 to the 4th power is 1296. Okay, and from that, we're going to subtract 8 multiplied by 6 to the power 3, or 1728, and minus 432. Okay, so thus 6 minus 432 are the coordinates of the, or of a, local min. Okay. The last thing was for us to go back and look at what we call the first derivative test. So use first derivative test. Okay, so this was where, that is, right, i.e. f prime at the critical value c is equal to 0. Okay, so f prime at c, we'll just go back and have a look at that right up here. Okay, so what we'll do is we'll take the first derivative and we'll find out from that if we're able to determine the nature of the max or min at that particular value. So let's go ahead and do that. So the first derivative, f prime at x, was, let's see, 4x squared onto x minus 6. Okay, so to determine where there are horizontal tangents, when we set that to 0, we're going to end up with the same situation, and that is to say we're going to have two solutions. So x belongs to 0 or 6. okay, in terms of f prime at x. Just going to go back and double check here. So we've already established that. What we do need to do is we need to establish whether or not, or what the tangents are doing on either side of the critical value we're questioning, which is f at 0. So let's test a value here. So let's look at something to the left of 0. So let's test f prime at 1. Okay, and from that, do some quick math here. We'll end up with 4 multiplied by 1 minus 6, which is negative 5. That's minus 20. If we test to the right, sorry, that was to the right. If we test to the left at minus 1, we're going to end up with 4 being multiplied by, let's see, minus 1 minus 6 is minus 7. And we have minus 20. Okay, so both to the left and the right, we can see that we have the same y value. So graphically, if we're to sketch this out, and if we're sketching, let's see the original function, or if we're simply looking at this particular, at the tangents at this point, okay? So the first derivative function is a cubic function with solutions at 0 and 6. So it's 0 and at 6. So we're going to see something along the lines of double 0 at the 0, right? Double 0 because of the x squared, dipping back down, and we know where this point is going to go at 6. We know that there is a local minimum there. So at x equals 1 and minus 1, okay, if we appreciate at those particular values, at here and here, these are y values of 20, we can now see that we do have a turning point, but in this case, it's no longer inconclusive, but we can see that we do have, for this particular function, that is for the first derivative function, we can see that this is a turning point for it. So this video is approaching about almost 25 minutes. I think we're going to chunk it up into another part. We do have to finish this one, and then we have to come back and go ahead and sketch the graph of the function, the quartic function. So let's stop it here, and then we'll do another part, or part 3.